Yeah, so in the last part of the class, we talked about lists, some applications of lists, and we're going to talk about, uh, as I promised, the standard data structures called stacks and queues. We will just talk about stacks first, and which are also a type of list. Each is a type of list, just that certain operations are not performed on the list. It's kind of more restrictive than the list. Okay. What is the stack? We call this a special ADT, and it's another abstract data type. And what are the operations that you can do? If I take this as a stack, I can push elements onto the stack, and I can pop elements of the stack. These are the various operations. I pop an element out of the stack. I can look at what is there on top of the stack, and I can check whether the stack is empty or not. Okay. There are many applications of stacks. And we will see where this is used. We already talked about recursive functions. You remember when we did the recursive function on some various recurrence problems that we looked at. Let's say I'm doing recursive function for factorial, and we have fact of n is equal to n star fact of n minus 1, and fact of 1 equals 1 is the termination criterion. Then clearly for every call of fact of n is n star is n star fact of n minus 1, which is n star n minus 1 star fact of n minus 2, and so on. And when n becomes 1, it'll all pop back. Okay. So what happens? Fact 1 gets computed first. Then we have fact 2 is 2 into fact of 1, and so on. So what happens is, in the calling function, if you look at it, it's n here, which calls n minus 1, n minus 2, and so on. Finally, it reaches 1. And then once 1 is completed, it goes back to the previous reference to the call for fact, and so on. And then it exits. So clearly what we need to do is, let's say this is the most recent invocation of fact, then it must keep track of, so it completes the last most recent one, then the next one, and the next one, and so on. So stack is an appropriate ADT for storing or doing the bookkeeping for recursive calls. What is the bookkeeping here? Basically keeping the return address of the previous function call for recursive function calls. We can also use it for other purposes. Let us say I want to, when you look at a C program, for example, you use flower brackets to enclose a piece of code, and you want to see whether the C program has balanced parentheses. Then this would be, again, let's say this is how it looks like. Then what I can do is every parenthesis can be put on the stack, and then when I get a matching parenthesis, which is a lateral inversion of this, then I pop things on the stack. So what happens is I can put things on the stack. Stack, as I already said, is the last in, first out. So let me call this 1, 2, and 3. So I put 1, 2, and 3 on the stack. And then as soon as I see 3, the first one, I pop this off the stack. Then I see the next one, I pop this off the stack. So once I pop this off the stack, what do I have? I have these two guys. Then when I see the next right bracket, I pop this next element out of the stack. Then when I see the last one, I pop the last element out of the stack. So what happens is stack becomes empty if there are balanced parentheses. You can check this out for, suppose I had only 2 like this, and there were 3 of these. Okay. Then this, let's say 1, this was 2, and then this one you saw, this got popped out, and as soon as you saw this, this got popped out. And when you see this, there is nothing, the stack is already empty. So what happens in this particular case? So you have this, you have one more here, and then you see this guy, then you pop this fellow off. You have one person on the stack, one bracket on the stack. Then you see the next bracket, you pop the one on the top, and if it becomes empty and you still have a right bracket, again the parentheses are not balanced. Okay, so we can use the properties of the stack to decide whether a pair of parentheses are balanced. You can also use it for various types of parentheses and ensure that things are balanced properly. For example, I can ensure that something like this, and let's say I have something like this, that this is not properly balanced parentheses. So stack can be used for various operations, but I'm going to talk about a particular application of stacks, which is very useful in performing arithmetic. And this application is the standard and well-known problem, conversion of infix expressions to postfix. We will see what are these type of expressions and why do we want to convert them to postfix in the first place. Okay. Infix is the standard, the way we write an expression, a plus b star c minus d is an infix expression, and the corresponding postfix expression will be a, B, C star plus and D minus. This is the postfix expression, and this is and each comes with its own rules of arithmetic, okay? This is an infix expression, okay? Now let's try and understand this. Now, let us assume that the the expression is being evaluated according to scientific arithmetic, like a scientific calculator, not an ordinary 4-function calculator. What's the difference between an ordinary 4-function calculator and a scientific calculator? In a scientific calculator, star comma slash have higher precedence than plus and minus. What's the meaning of this? That if an expression has either star or plus, they will be evaluated before the plus. So what's the meaning of this? This expression, if I put brackets to ensure that the expression gets evaluated completely correctly, this is what it would evaluate. This is what a scientific calculator does. That means if I see two operators, plus and star here, star has higher precedence, the star will be evaluated and then the plus. Another thing that also that it shows us, we already know implicitly, there's an implicit assumption that expressions that operators in an expression associate to the left. Let me also tell you what this means. What do we mean by left association here? What we're saying is, if I have an expression a minus b minus c, then this is equal to a minus b minus c and not a minus of b minus c. This left associative and this is right associative. Okay. So this is what we also know. So implicitly the associativity is assumed in an expression. Now, so what happens over here? So given this, similarly, if I take a plus b star c minus d, this will be evaluated before the subtraction is performed. Okay. So now, actually, we have seen this some time back, and I've just given it to you in passing. Expressions in a language, although this is outside the scope of this course, you will be doing it in your compiler's course, are represented by a grammar in a language. In a language, as I had discussed earlier. And the way we write this is, say, expression is defined as, is a recursive way of representing it. And we have add operator term, and we have or a term by itself. And we talked about this in the context of proving correctness of programs when we're looking at assignment statement, where the left-hand side is a variable and on the right-hand side you have an expression. Term, mult operator, factor, and or it can be a factor, and a factor can be a number or, for the time being, let's assume it's a or a variable name, and we know the definition of a variable name. Let's assume that we know. And add operator, both plus and minus have same precedence. Multiplication operator consists of star, slash, and percent in the context of C for that matter, and remainder when divide two numbers, and so on. Why am I talking about this? This actually says that if I have a plus b star c plus c minus d slash f plus g, then this is the expression, this is the operand 1, and this is operand 2, and this equation, this grammar actually says that we perform operand 1 minus operand 2. So if you notice how we're evaluating the expression, we're starting from the right. Look at this plus here. This whole thing is evaluated, and to that we add the value of g. Okay, and then what do we do? Now you look at this part. This is again an expression now because there is a recursive definition over here. So I will do a plus b star c plus d c b plus c, sorry, a star b plus c plus c minus d. Okay, again the operator, expression, term. Okay, and we keep recursively working on this particular expression evaluation over here. So now what we see is when you're given an infix expression, all these properties of operands and operators are implicit according to this particular grammar that we have. Okay. This grammar is what we're going to use to evaluate an expression. Now, on the other hand, let's see how a postfix expression gets evaluated. Let's take that A plus B star C minus B. And I said the postfix expression for this infix expression is plus and D minus. And if you notice, there is no implicit bracket. Here, for example, there was an implicit bracket here. No implicit brackets are necessary. I'll tell you why this is so. Brackets are necessary for evaluating this expression. So let's see how these, of course, the one assumption that is of course there, that the operands are, the operators are binary. So what we do is, we start from the right of this expression. So since they are binary, it requires two operands, operand 1 and operand 2 to evaluate. Okay. And then what we do is, the most recent operand that you see from the right is operand 2. And after that, whatever you see is operand 1. So now let's start looking at it from the right. So what I do is, let's say I keep this value of minus here. I keep this value of minus here, and I keep the value of, let's say D is, because there are no two operands here, but another operator that has come. So I'll keep it here. Then what I will do is, I see an operator here. I'll put this guy over here too. And next I see an operator star. Let me repeat this. I saw minus, and then I'm expecting two operands, but I'm seeing two, but I'm seeing one operand, which I have D over here, and I'm seeing an operator, another operator. So I'm just, let's say I'm putting it on, the first one came here, I'm putting it here, and then I have put this guy over here. Now this operand D, okay, and I've got the plus also. Next, what do I see? I see a star. But as soon as I see a star, I see two operands, one beside the other. So my operand 1 is B and operand 2 is C. The first most recent operand is operand 2, and the next operand that I see is operand 1. I perform B star C. Okay? So I get this star over here, and I see that the next two are operands. I perform this evaluation, and then I just say, okay, I have A here. I'll put B star C back here. Okay. So now, let me rewrite this properly. A and B star C are there. I still have the D guy, is separate. Now I look at it, I have an operator. So if you combine this, assuming that B star C is evaluated, what do we have? We have A, B star C. Now if I go back and look at the expression, plus and minus, plus and then D and then minus. So now I still have keep the minus, I keep the D, I look at the plus here, and now I have two operands. I perform A plus B star, A plus BC star is one operand. Now I have the second operand, have the minus, and I can perform A plus B star C minus D, which will be the value of the expression. So if you notice, we really did not, all that we learned was we have to process the expression from the right. If there's an operator, look for two operands. As soon as you see two operands, perform the operation, assuming that the most recent operand is operand 2 and the later operation is operand 1, and perform this operation between the two of them, and then store it back in the same place. And then you keep repeating this while there are no operators or operands that are left. Okay, so most importantly, we did not have to worry about, the rules for postfix expression evaluation. Have to worry about either precedence or associativity. Okay, so this is the good part about converting any expression, and you can do the same thing with bracket also. Suppose I have a plus b minus c star b, or let me take minus, it's a more nice thing, something like this. Then what do I have? I have a over here. Then I have b, c, d star, this minus, let me make this plus here, plus and minus. Okay, this is how the postfix expression will be. Okay, no brackets either. Okay, so the good part is a postfix expression is very easily evaluatable, and what we actually did, the way we perform these operations, actually uses a stack. But first we have to see how do we convert an infix expression with its appropriate associativity to a postfix expression. Okay? And of course, what happens when you, there's one operator which is associates to the right. I'm going to talk to you about this. And if I write it as x hat, y hat, z, it's actually x hat, y hat, z, and not x hat, y hat, z. This is not correct. Okay, so we'll stop here and continue with stacks in the next week.